Calcium magnesium silicate oxides, which are prevalent in certain rocks, react spontaneously with carbon dioxide to produce mineral carbonates, such as limestone or magnesium carbonate. Mineral carbonates offer long-term storage because they are stable under ambient temperatures and pressures, and can serve as construction materials or as filler in abandoned mines. To fix a metric ton of carbon dioxide in carbonates requires from 1.6 to 3.7 metric tons of silicon oxide rock. Nonetheless, the Earth's crust contains more than enough of these silicon oxides to react with all the carbon dioxide released from combusting the Earth's entire reserves of fossil fuels. Natural carbonation, however, is prohibitively slow. Accelerating this process to acceptable rates involves mining rocks containing silicon oxides, crushing and grinding them, and removing impurities. Then, the silicon oxide paste dissolves in a mild acid solution and carbon dioxide is bubbled through the solution at high temperatures and pressures. Finally, the process stream filters fine carbonate particles from larger unreacted silicon oxide, disposes of the carbonates, returns the silicon oxides to the reaction vessel. These procedures consume 30 to 50% of the energy generated by a power plant. Together with a 10 to 30% energy penalty for carbon dioxide capture, a power plant equipped with mineral carbonation, CCS, in comparison to a plant without CCS, would expend nearly double the energy for operations. As a result, costs for mineral carbonation, CCS, are several times other methods. Little wonder why mineral carbonation CCS has yet to be implemented on a commercial scale. Earth's oceans are vast, covering over 70% of the planet's surface at an average depth of 3,800 meters. Injecting carbon dioxide into the deep ocean would isolate it from the atmosphere for several centuries and halve peak atmospheric concentrations. Eventually, after about 2 millennia, carbon dioxide concentrations in the atmosphere and oceans would come back into equilibrium. Therefore, oceans can offer long-term, but not permanent storage. Several mitigation strategies envision that electric power plants would pump captured carbon dioxide down pipelines into the ocean depths. Alternatively, tanker ships carrying carbon dioxide would release it at depth or carry the carbon dioxide to platforms that release it at depth. Finally, some plants would convert carbon dioxide into calcium carbonate and dissolve it in seawater for release at depth. The fate of carbon dioxide in water is complex, both in its dissociation into different carbonate forms and its transitions among gas, liquid, and solid phases. Hydrostatic pressures increase and temperatures drop with depths in oceans. Injected carbon dioxide remains a gas until about 400 meters deep, at which point it becomes a supercritical fluid. Below 3,000 meters, liquid carbon dioxide becomes denser than seawater and sinks. Injection of carbon dioxide into deep water therefore may establish carbon dioxide lakes and depressions on the sea bottom. Such lakes would delay the dispersion of carbon dioxide into the surrounding environment. Large-scale injection of captured carbon dioxide into the oceans would influence sea life. High carbon dioxide concentrations themselves can interfere with aerobic respiration. Moreover, liquid carbon dioxide behaves as an organic solvent that may prove toxic to certain organisms. Finally, dissolution of carbon dioxide into its various bicarbonate and carbonate forms would acidify the surrounding water, and sea life would respond to these pH changes. Nonetheless, we have such limited knowledge about life in deep oceans that we cannot anticipate all the consequences of massive carbon dioxide injections.